Hello and welcome to Engineers Mindset Academy. Alright, so in today's video, we are going to continue with the question 5 of the 2023 Applied Mechanics Examination question of the Rivers State University, Port Harcourt, Nigeria. So let's take a look at the question. Question says, determine the force P required to raise the block B in figure 5. Given that the coefficient of static friction is 0.35 between all surfaces of contact. All right, so you're given the wedge system here. This is actually a friction and wedge analysis. So this is the wedge. Actually, the block A is simply the wedge, and the block B is the load which we are lifting by the application of what this effort or this little load P. So the block A actually is the wedge. Okay, when you apply a load on this block A, when you apply a force, when you apply an effort or a force on this block A, which is a wedge, it pushes this load, block B, up the plane or down the plane, which is the idea of wedge friction. Now, we are asked to find the value of this force or the magnitude of this force, which is propelling what? This motion. Now, in analyzing a wedge friction, all you need to do is simply consider each of the diagrams separately. For instance, the block A and the block B, you consider them separately, do their equilibrium diagram, and employ all the equilibrium equations you know on each of these diagrams. So we are going to start with block A. As usual, whenever a problem is given to you in applied mechanics, you always start with what? Your free body diagram. So you start with FBD of block A, free body diagram of block A. So we are starting with block A. You simply draw out the given block and show all the hidden forces on the system. So you have this is block A, something like this. You have something like this to be block A. All right, the angle here is 10 degrees. Sorry, the angle here is 10 degrees, as can be seen there. Angle of inclination is 10 degrees. Now, mind you, block A is resting on a surface, and whenever two surfaces are in contact, there is bound to always be a normal reaction at 90 degrees to the surface in contact. Whenever two surfaces are in contact, there is bound to be a normal reaction. I have this block A resting on this surface. So far block A is resting on this surface, there is always going to be a normal reaction. That reaction always acts at 90 degrees to the surface. So we have a normal reaction here. Call this normal reaction N1. It is always at 90 degrees, as can be seen, to this surface. So whenever two surfaces comes in contact, there is always a normal reaction. Similarly, we have a force P here. So you indicate there's a force here, a horizontal force here, and the magnitude is P, unknown. And also, we have block B resting on block A. They are making contact at this point. They are making contact at this surface, okay? Block B and block A are making contact at this surface. And I've already said, whenever two surfaces come in contact, there is always bound to be what? A normal reaction. So you put in the normal reaction, always it must be at 90 degrees to the surface. So we have this normal reaction at 90 degrees to the surface, as can be seen here. So this is at 90 degrees to this surface. So call this normal reaction N2. All right, we can take this off. Okay, so this is the free body diagram, but it doesn't end there. Now, on application of this load P, if you apply this force on this wedge or block A, what happens is that this force causes block A to move to the left, because this force is directed where? To the left. Okay, so we can analyze that over here now. This force is directed to the left, so which means it will cause this block A, okay, this is block A, it will cause block A to move to the left, which means the motion of block A is moving towards the left. And remember the idea of friction. Friction simply means an opposite force or an opposing force. So if I am moving to the left, then there is a force that will oppose my motion. That force will move here to the right. That force is called a frictional force. Since I have a normal reaction here and these two surfaces are in contact, again, whenever two surfaces are in contact, one, there is bound to be a normal reaction. Secondly, when a load is applied, there is always bound to be what? A frictional force on each of those points of contact. On each of the points of contact, there is bound to be what? A frictional force. So if this load is propelling this block to move to the left, which means on this surface which I have two surfaces in contact under here, there is bound to be a frictional force that will move here to the right. So simply call this F1. Since here is N1, call this F1. Since this load is moving to the left and this is purely a horizontal plane, that means I'm also going to have a frictional force that moves here to the right. To the right, yes. Okay, so we simply call that F1. Similarly, this surface is in contact. Remember, these two surfaces are in contact. Block B and block A are in contact at this surface. Since they are in contact, which means if this load is pushing this wedge to move to the left, on this contact surface, I will also have a frictional force because motion on this plane now is down. Motion on this plane is inclined, sorry. Because motion on this plane now is inclined. Since motion on this plane is inclined, if this load or this force P is propelling block A to move to the left, it means I will have a frictional force that will move here up the plane to the right, but now up the plane, because wherever two surfaces comes in contact, there is a normal reaction, and if a load is applied on those or on the body, then the surfaces that are in contact will experience frictional force, and frictional force is always opposite the motion. So if this load is applied here and motion on this plane is inclined, because this is an inclined plane, that means frictional force will act here up the plane. So it means we are going to be having frictional force up the plane. So call this what? F2, since this is N2. Call here F2. So in all, whenever two surfaces are in contact, there is not just a normal reaction, but there is also bound to be what? A frictional force. If a load is applied, there is bound to be a frictional force on all the surfaces in contact, and that frictional force will act against the what? Motion or direction of motion of the force. So this becomes your free body diagram for block A. Now, all you need to do is simply employ your equilibrium equations. What are the equilibrium equations? I've done lots of videos covering equilibrium equations from beginning of applied mechanics down, from two-dimensional force analysis down to shear force and bending moments, down to friction and wedge. I've covered all of that, so you can do well to watch all the videos for proper understanding. So you simply employ equilibrium equation. So from equilibrium equation, okay, from equilibrium equation, the first equilibrium equation, we have summation of horizontal forces, summation f of x is equal to what? 0. Now, in the case of friction, when we did shear force and bending moment, I said summation f of x is equal to 0 when forces that point to the right is positive, whereas forces that point to the left is negative. But in the case of friction, it is not so. In friction, force is always positive in the direction of motion. So if the direction of motion is to the left, then every force that points to the left is what? Positive, because at that point, all the objects are moving in favor of what? The force. So which means forces that point to the right becomes negative. So that's the difference between friction and the normal, maybe shear force and bending moment, which we talked about earlier. So summation f of x is the first equilibrium force. Summation of all horizontal force is equal to 0. Now we are going to consider force that moves in the direction of motion to be positive. And we know that what is actually causing motion on block A is this force P. It is when this force is applied that this load is being lifted up. Block B can now be either lifted up or what? Lifted down. Okay, so everything on this system depends on what this load, which means the motion of the block A is where? To the left. So in that case, force that point to the left are considered positive, whereas force that point to the right are considered negative in this case, because motion is where? To the left. All right. Another thing to consider is, notice now that motion here is inclined. I have normal reaction 2 and frictional force 2. They are both inclined. Whereas motion here is purely, like frictional force here is purely horizontal. The normal reaction N1 here is purely vertical. The load itself P is purely what? Horizontal. So all we need to do at this point is, these forces that are inclined, N2 and F2, all we need to do is to what? Resolve them to be what? Purely horizontal and purely vertical. That is all we need to do. So you simply resolve these forces to be purely horizontal and purely vertical. How do you do this? By simply drawing an imaginary line. So you draw an imaginary vertical line. Okay, something like this. You can draw an imaginary vertical line or a broken line. Now, the angle between the normal reaction and the vertical line is always taken as the angle of inclination. The angle between the normal reaction and the vertical line is always taken as the angle of inclination. So if this is a vertical line and this is a normal reaction, then that means this angle between the normal reaction and the vertical line is always taken as the angle of inclination, 10 degrees. So this angle is simply 10 degrees. Okay, that is not visible enough. We can do that over here now. So I have my normal reaction. Now, mind you, another thing to note is the normal reaction force and the frictional forces are always at 90 degrees to one another. Keep that in mind. The normal reaction force and the frictional force are always at 90 degrees to one another. So I have the normal reaction force, I have the frictional force. They are always at 90 degrees to one another. Call this is F2. Now I said you draw an imaginary what? Vertical line. Something like this. Okay, you can also make this horizontal. So you have now, this is y-axis and this is what your horizontal. So this has now automatically become what? A vertical and a horizontal plane. So which means I can now resolve this normal reaction which is inclined to be vertical and what? To be horizontal. Same thing with the frictional force. I can resolve frictional force to be what? Vertical and to be horizontal. Then I said the angle between the normal reaction and the vertical line is always taken as the angle of inclination, 10 degrees. So indicate that 10 degrees. So if here is 10 degrees, remember angle of the quadrant is 90 degrees. That means from here to here alone is simply what? 80 degrees. Similarly, the normal reaction and the frictional force always makes an angle of 90 degrees to one another. Keep that in mind. So we have this is the normal reaction line, this is the frictional force. Two of them are making an angle of what? 90 degrees. So if here is 10 degrees, that means this is also what? 80 degrees. And hence, this angle here is also what? 10 degrees. So all we need to do at this point is resolve the frictional force and the normal reaction force purely vertical and purely horizontal. Okay, so we can do that over here now. Now, I've said in my two-dimensional force analysis videos that to resolve a force in a vertical axis or horizontal axis, all you need to do is hold the tip of the arrow of the force and pull it to meet any of the direction you want to incline or you want to resolve it to, sorry. Pull it to any of the direction you want to resolve it to. Now, the first thing to consider is the direction of the arrow. If it points to the right or it points to the left. But in this case now, since we are talking about friction, it must point to the left to be what? Positive, because the motion of the block is to the left. So if it points to the left horizontally, it is positive. If it points to the right, it is negative. Then if it passes through any angle to get to that particular direction you're resolving to, then it becomes what? You multiply the force by cosine of the angle it passes through. So we did all of this in our two-dimensional force analysis videos. All right. Now, I want to resolve the normal reaction to be purely vertical. Remember the direction of the arrow. It is pointing downwards. So you pull this force to meet, this is the vertical line. Now, you pull the force to meet the vertical line closer to each quadrant. This force is on the second quadrant. The vertical line close to the second quadrant is what? This particular line and not this one under. So you can't pull this force all the way to this point. You cannot. It has to be the vertical line closer to the quadrant. So if I pull this force to meet this line, observe the arrow direction. This arrow points where? Downwards. This arrow points downwards. If I pull this force to meet the vertical line, this is the vertical line closer to each quadrant. This arrow points downwards. So which means vertically, this force is pointing downwards. And whenever a force points downward vertically, that force is negative. So it means that my normal reaction points vertically downward. So you can put it down here. It points vertically downward and it passes through what? This angle, 10 degrees. It moves all the way from here to this point to meet the vertical line, covering this angle, 10 degrees. So you multiply the force by cosine of the angle it passes through. It becomes what? N2 times cos 10. It's as simple as this. Then resolving N2 now, still the normal reaction force horizontally. Hold the tip of the arrow, pull the force to meet the horizontal line closer to each quadrant. The horizontal line closer to this second quadrant is simply what? This horizontal line. Now, observe the arrow direction. If I pull this force all the way from here till it meets this horizontal line, Remember, the normal reaction is pointing outward here, is pointing inward, sorry, here. So if I pull it to meet this horizontal line, this force points where? To the right. This force points to the right, something like this, because the arrow sign is here. So if I pull this force till it meets with this line, this force points to the right. So you have something like this. Force is pointing to the right. And it moves all the way from here to this point, covering this angle 80 degrees. So you simply multiply the force by what? Cosine of the angle it passes through. Hence, you have N2 cos 80. So this is now the vertical and horizontal resolution of what? The normal reaction force. Same thing for the frictional force. Hold the tip of the arrow of the frictional force and pull it. Now, I want to resolve this force horizontally. Okay, so you pull it to the horizontal component closer to each quadrant. This force is on the first quadrant. The horizontal component closer to this quadrant is simply what? This particular one here. So you pull this force, observe the arrow direction now. If I pull this force all the way till it meets this horizontal line, this force, observe the arrow direction, it points to the right. This force points to the right. So I have this force pointing to the right. And it moves all the way from here to this point, covering this angle 10 degrees. Since it covers 10 degrees, then you multiply the force by what? Cosine of the angle it passes through. Hence, you have this to be what? F2 cos 10, always multiply by cosine of the angle it passes through. Now, resolving this force vertically, still the same thing. Hold the tip of the arrow of the force, pull it to meet the vertical line closer to each quadrant, which is this particular one now in this case. Observe the arrow direction. This force still points where? Vertically upwards. It points vertically upwards and not downwards. So you have this force pointing vertically upwards. Okay, so I'm bringing it down because I can't draw it here. Okay, so you have this force pointing vertically upwards when it gets to this plane. The arrow is pointing out, so on getting to this plane, it points where? Vertically upwards. And it moves all the way from here to this point, covering this angle 80 degrees. So which means it becomes what? F2 times cos 80. You have this. So you have now successfully resolved these two forces, the normal reaction force and the frictional force to where? You resolve them to horizontal and vertical components. Now everything on the plane are purely what? This is purely vertical, purely horizontal, purely horizontal. Everything now are purely vertical and purely horizontal. You can now employ this equation. So summation f of x, this is now the direction of motion. Every force that points to the left must be positive. So which means frictional force must be negative. And that will tell you that frictional force in this case now will point to where? Will point to the right. Because if motion is positive in the direction of force, then frictional force should be what? Negative, because it opposes what? That motion. But let's sum them up now and see. So we have force P, purely horizontal, pointing to the right, positive. You pick it out, P. Then you have frictional force F1 pointing to the right. Are you seeing now that it is negative because it is pointing where? To the right, against the motion. You have minus F1. Also, you have this frictional force F2 cos 10, also a frictional force pointing horizontally to the right. So always your frictional force will always give you what? A negative value, because it is always opposing motion. So since it moves to the right, it becomes negative. So I have minus F2 cos 10. And I have the normal reaction also pointing to the right. So it's negative. You have N2 cos 80. So you have minus N2 cos 80. So the whole of this is simply equal to 0. These are all the horizontal forces we have on that system. All right, so you have P minus F1 minus, let's obtain what is cos 10 and what is cos 80. So cos 10 is approximately 0.98, so it becomes minus 0.98 F2 minus, let's obtain cos 80. Cos 80 is approximately 0.17, so this becomes minus 0.17 N2 equals 0. Okay, so you can simply say P is now equal to, let's send all of these terms over to this side of the equation. Negative signs cross equal to sign becomes positive. So I simply have F1 plus 0.98 F2 plus 0.17 N2. Okay, but have it in mind that frictional force is always given as the coefficient of static friction multiplied by normal reaction. This is relationship between frictional force and the normal reaction. It is always coefficient of static friction multiplied by the normal reaction. So which means F1, frictional force 1, will simply be what? Mu1 times N1. Similarly, F2 will be equal to mu2 times N2. But let's pause and look through the question. The question says, given that the coefficient of static friction is 0.35 between all surfaces of contact, so which means the coefficient of static friction at all surfaces of contact are what? The same. It doesn't change. So this simply means that mu1 is equal to mu2 and is also equal to what? 0.35. The two coefficients of static friction are what? The same. It doesn't change. So we can now effect that into this equation in place of F1 and in place of F2. All right, so I think I can wipe this portion of the board. I don't need this again. I don't need this part again. Okay, so let's now start from here. You have P is equal to F1, and in place of F1, F1 is, okay, let's do this over here first. So this means that F1 is equal to, we said mu1 times N1, and mu1 is something as 0.35. This becomes 0.35 was N1, where 0.35 stands for what? Coefficient of what? Static friction. Similarly, F2 is also what? Mu2 times N2, where mu2 is still what? 0.35. So you simply have 0.35 times N2 in place of F2. So in place of this F1 in this equation, P equals 0.35 times N1 plus, here we have 0.98 F2, and F2 also is what? 0.35 times N2. So this becomes 0.98 times 0.35 N2. Okay, and finally plus 0.17 N2 plus 0.17 N2. Okay, so P is equal to 0.35 N1 plus, let's evaluate, 0.98 multiplied 0.35. That gives us approximately 0.34. So you have 0.34 N2 plus 0.17 N2. So these two can add 0.34 N2 plus 0.17 N2. We have P to be equal to 0.35 N1 plus, let's add up these two now, plus 0.17. That gives us 0.51 and 2. So you can keep this equation for P, okay, or we can take it down here. So P is actually 0.35 N1 plus 0.51 N2. Call this equation 1. All right, so all we need to do now is very clear. This is the value of P, but we need to find N1 and we need to find what N2 is. If we're able to get these two and put them back into this equation, we can find the value of P. So we are done with what? Horizontal summation. Okay, that's the first equilibrium force. The next equilibrium force is now to sum here vertical forces together. So we can still do that over here. All right, so the second equilibrium force is summation F of y is equal to 0. Now, since motion is neither upwards nor downwards, then the law for summation of vertical forces remains the same. Vertically upward force remains positive and downward force remains negative. Since motion is not in this direction, then this law maintains its own condition. Vertically upward forces are positive, downward forces are negative. So all you need to do is simple. You pick out the first free body diagram of the first block or the first diagram, then carry out your equilibrium equation. Summation of horizontal force, summation of vertical force, you're done. You move to the next diagram, do the same thing, summation of horizontal force, summation of vertical force, you're done. Then try to relate everything you get from it and see where it leads you to. Okay, so let's now consider the vertical reaction for what? This same block A. For the vertical reaction, I have my normal reaction N1 pointing vertically upward, so it's positive. You indicate N1. And All right, so I'm going to pause the video here and bring back the result we obtained when we resolve N2 and F2 in both vertical and horizontal component. I wipe it over here, so I'm just going to redraw it over there and use the vertical component to solve over here. So I'm going to pause the video here. All right. All right, welcome back. So earlier we resolved N2 and F2 and we obtained that the vertical component for N2, since they are all inclined here, the vertical component gave us what? N2 cos 10. We did this earlier. And for F2, each vertical component gave us F2 cos 80. So we are now on summation of vertical components. And I said, you look at the system, block A in this case now, sum all the vertical components together and equate them to 0. I have N1 pointing upwards. Since it's pointing upwards, it becomes positive. So you simply put down N1. Now, considering this phase now, this P is purely horizontal and does not have a vertical component. So you leave it, it's a horizontal component. Then you move over towards here, the normal reaction and the frictional force, which will result over here. So we obtain the normal reaction is pointing where? Downwards. Since it's pointing downwards, it becomes negative. The value is what? N2 cos 10. So you simply have minus N2 cos 10. You put this down. Similarly, I have force F2, frictional force F2 pointing upwards. Since it's pointing upwards, it becomes positive, and the value gave us F2 cos 80. So you have plus F2 cos 80. So these are all the vertical forces on this system. You simply equate this towards 0. So you have here N1 is okay minus N2. Now cos 10, okay, cos 10, we obtain cos 10 earlier as 0.98. So this becomes 0.98 N2 plus, I have F2 here, and F2, remember we obtained F2 as 0.35 N2. So in place of F2 here, you have 0.35 N2 multiplied by cos 80, okay, and cos 80 gave us 0.17. Cos 80 gave us 0.17, so multiply by 0.17. The whole of this is equal to 0. Okay, so N1 minus 0.98 N2 plus, now let's obtain 0.35 multiply 0.17. That gives us 0.06 N2, and this is equal to 0. So we simply evaluate. This is 0.9 minus 0.98 N2 plus 0.06 N2. So let's evaluate that too. Minus 0.98. That simply gives us, you have here N1 minus 0.92 N2, and this is equal to 0. So this simply means that, of course, minus 0.98 N2 plus 0.06 N2 gives us minus 0.92 N2. So you can simply send minus 0.92 N2 over to this side of the equation. So this implies that N1 is equal to negative sign, cross and equal to sign becomes positive. So I have 0.92 N2. So you can simply call this equation 2. Okay, so this equation is for what? The normal reaction. You can call that equation 2, which means we have gotten a value for the first normal reaction, N1. Hence, you can put that value in place of N1 here, and you have N1, you have every time set to be in terms of N2. Okay, you can put it over here. Okay, let's do that at once. So putting N1, since we know the value of N1, substituting N1 into equation 1, you're going to have P, okay, to be equal to, we had it here to be 0.35 N1. So this is 0.35 N1, but N1 has a value of 0.92 N2. In place of N1, we have 0.92 N2, okay, plus, you have here 0.51 N2, 0.51 N2. Okay, so let's evaluate. This simply gives us P to be equal to 0.35 multiplies 0.92. That gives us 0.32 N2 plus 0.51 N1. So let's add this all up now. 0.32 plus 0.51. All right, so P becomes 0.32 N2 plus 0.51 N2. That gives us 0.83 N2. Hence, you can keep that equation somewhere for P2. You can keep that equation somewhere for P. All right, so P is simply equal to 0.82, 0.83 N2. All right, so you can simply call this equation 3. So all we are looking for now is what? N2. So we are done with equilibrium analysis for what? Block A. We can now clean block A and write the free body diagram or draw the free body diagram of block B and analyze and see what we are going to do. So the only thing we are looking for now is what? N2. If we're able to get a relationship for N2, then we are good to go. All right, so we can wipe every other thing now and redraw. All right, so now we move to a free body diagram of block B. So you pull out the block B now, and block B you have something like this. All right, remember you have a weight here of 1000 newtons. Okay, remember these two surfaces are in contact, block B and block A are in contact. Whenever two surfaces are in contact, you always have a normal reaction at 90 degrees to that surface. So you have a normal reaction at 90 degrees to this surface. Now, mind you, this normal reaction here is the same normal reaction when you consider block A. Remember, we call that normal reaction N2. So the normal reaction here is the same normal reaction when we consider block A. But in this case now, it is now opposite. It still maintains the same theory. It must be at 90 degrees to the surface. So it still remains N2. All right. Similarly, you have this block to be resting on this surface. So whenever two surfaces comes in contact, what happens again? You have a normal reaction. So you have another normal reaction at 90 degrees to the surface. So which means this is going to be now horizontal. Okay, because it must be at 90 degrees to the surface, as can be seen here. It must always be at 90 degrees to the surface. Now, since this is the third normal reaction we are introducing now, you simply call this N3. Remember, the first one was here between block A and this surface. Second one was between block A and block B, which still remain here as N2. So this is the third normal reaction. And finally, as this load P or as this force P is propelling the block A to move to the left, observe please, if block A is moving to the left, this is an inclined surface. So the aim of this wedge is to pull this load up this plane. So if this block A is compelled by this force to move to the left, it means that the motion of this block will move here. Block B will move to the right. Motion of block B will move to the right. Incline on this incline as well, it will be moving upwards to where till it gets to this top. That's the essence of this wedge. Okay, so if this block or this load is pushing this block to move to the left, it means the block B is moving where? To the right because of this inclined surface. So the motion of block B is actually where? To the right. Now, it means that motion on the incline is moving upwards on block B. Motion of the incline on block B is moving upwards. That means frictional force on this block B will act where? Downwards. It means frictional force on the block B will act downward because on this incline, motion on block B is moving upwards. So if motion is moving upwards, then frictional force on this block will move down the plane. So you have this to be what? It still remains what? F2. Same thing because it's still the same contact surface block A and block B. So it still remains F2, but now on block B, F2 is acting downwards. Similarly, on this portion, as this object is moving up the plane and since here is purely vertical and not inclined, that means the motion of this object on this side is moving where? Upwards, purely vertical, upwards. Motion here over the incline is moving inclinedly upwards, but at this vertical plane, the motion is purely where? Vertical, moving upwards. That means frictional force will act where? Downwards on this plane. Frictional force on this side of the block will act downwards. So you have another frictional force acting downwards. Call this F3. So just like we did in the first, you have now F2, of course, F2 and N2 are inclined. This is purely horizontal. This is purely vertical. The wave itself, 1000 Newton, is also purely vertical. So we need to what? Resolve these two reactions. Okay. We need to resolve the normal reaction. Let me draw this well a bit. Okay. N2. So we need to resolve the normal reaction and the frictional force to be what? Purely vertical and purely horizontal. So as usual, like I said, the normal reaction and the frictional force are making an angle of 90 degrees to one another. So you have the frictional force, which is this, F2, which is this, and you have the normal reaction. They are at 90 degrees to one another. So you have the normal reaction, okay, which is this. Call this N2. So they must always be at 90 degrees to one another. All right, so as usual, I said simply draw an imaginary vertical line. So you can use a broken vertical line for that. You draw an imaginary vertical line, okay, something like this. Now, I said the angle between the normal reaction and the vertical line, this is the normal reaction. Angle between normal reaction and the vertical line remains the angle of inclination 10 degrees. The angle between the normal line and the vertical reaction remains the angle of inclination 10 degrees. Similarly, okay, if here is 10 degrees and angle on a quadrant, you can as well do this to automatically convert this to be what? Purely vertical and purely horizontal. So if here is 10 degrees, that means the angle here is 80 degrees. And since the normal reaction and the vertical line makes also, if here is 10 degrees, that means here is also what? 80 degrees. And if here is 80 degrees, that means here is 10 degrees. Okay, let me trace this out a bit. That means this angle here is 10 degrees. Okay, this is F2. All right. So we need to now what? All we need to do is resolve F2 vertically and horizontally, and resolve N2 similarly vertically and horizontally. To resolve F2 now, you already know the rules. Hold the tip of the arrow. I want to resolve this force vertically. I'll pull this force to meet the vertical line closer to each quadrant. The vertical line closer to the third quadrant where this force is found is this vertical line. So which means I'm going to pull this force all the way to meet this vertical line. Observe the arrow direction. This force points in this manner, pointing outward. That means if it aligns with this vertical line, it will point where? Downwards. It will point vertically downwards. So you have the value of the force. The force points vertically downwards, and it passes through where? This angle. It moves all the way from here to this point, covering this angle 80 degrees. So you multiply the force by what? Cosine of the angle it passes through. That means this becomes F2 times cos 80. Similarly, resolving this force horizontally, hold the tip of the arrow of the force, pull the force to meet the horizontal line closer to each quadrant. In this case, this is the only horizontal line closer to this quadrant. So you pull this force to meet this horizontal line. Observe the arrow direction. This force is pointing out in this manner, which means on getting to this point, it will point to the left. This force is pointing out, which means if you're able to align this force with the horizontal line, it points to the left. So you have the force pointing to the left, something like this. You have the frictional force pointing to the left. All right, and the value, since it passes through this angle 10 degrees, you simply multiply the force by cosine of the angle it passes through. So this becomes what? F2 cos 10. So you have F2 cos 10. So that's the resolution of the frictional force. We'll move now to the normal reaction. This is the normal reaction. If I resolve this force horizontally, hold the tip, observe this arrow direction it is pointing out. If I pull this force to align with the horizontal line, this force points where? To the left. This force points to the left. So you have the force component pointing to the left because the force itself is pointing out. So if you resolve it to meet this line, it points to the left. And since it points to the left, it covers what angle now? It moves all the way from here to this point, moving all the way from here to this point, covering this angle 80 degrees. Covering that angle 80 degrees. So which means you multiply the force by cosine of the angle it passes through. That becomes F2 N2 cos 80. It becomes N2 cos 80. Vertically, you hold the tip of the arrow of the force, pull it till it meets the vertical line. Observe the arrow direction pointing out. That means between the vertical line, it points vertically upward. So you have the force pointing vertically upwards. Something like this. It points vertically upwards. And it moves all the way from here to this point, covering this angle. This angle is 10 degrees. Same thing as here, 10 degrees. So it becomes N2 cos 10 degrees. So that becomes the resolution of what? The normal reaction and the frictional force in both vertical and horizontal components. So let's start with the horizontal resolution. Summation f of x is equal to 0. Now, mind you, the motion of block B is to the right. We already explained this earlier. Block B has its motion now to the right. So which means every force component that points horizontally to the right is positive, whereas those that point to the left is negative because the motion of block B is to the right. Alright, so summation f of x is equal to 0. Force that points to the right considered positive. Those that point to the left are considered negative. So we look through the structure and let's pick all the horizontal components. I have N3 pointing to the right, so it's positive. We put it out, N3. I have, okay, from this resolution, from the resolution, I have F2 cos 10 pointing to the left, so it's negative. F2 cos 10 pointing to the left, so minus F2 cos 10. Similarly, I have N2 cos 80, N2 cos 80 pointing to the left, okay? So minus N2 cos 80. So this is equal to what? 0. All right, so that means not forgetting F2, remember, F2, we did that earlier, is equal to mu2 N2. And since coefficient of friction is same at all surfaces, then it means this is actually 0.35 times N2. Similarly, F3 will also be what? Mu3 N3. And since the coefficient of friction is same at all surfaces, then mu3 remains 0.35 times N3. You have something like this. Okay, so let's put all of that together. N3 minus, in place of F2, F2 becomes 0.35 times N2 multiplied by cos 10. Now, what is cos 10? Cos 10 gave us 0.98 minus N2 cos 80 gave us 0.17, and this is equal to 0. So this is N3 minus, let's obtain 0.35 multiplied 0.98. 0.34 N2 minus, this is 0.17 N2, and this is equal to 0. So you have N3. Now let's evaluate minus 0.34 minus 0.17. That gives us minus 0.51 and 2 to be equal to 0. So which means from here we can make N3 subject by sending minus 0.51 N2 over there. So this simply implies that N3 is simply what? 0.51 N2. So you can call this equation 4. So let's put that equation 4 over here. N3 equals 0.51 and 2. This is equation 4. All right, so having done this, next thing to do now is summation of vertical forces. So we can still do that over here. We have to now consider summation of vertical forces. All right, so once again, summation f of y equals 0. And since motion is neither vertical nor horizontal, then it means vertical component holds its law positive, vertically downward force is negative. Okay, so we have F3 pointing vertically downwards, it becomes negative, minus F3. We have 1000 newtons pointing vertically downwards, so it's negative, minus 1000. We have, from the vertical resolution here, we have F2 cos 80 pointing vertically downwards, so it's negative, minus F2 cos 80. Similarly, from N2 resolution, we had N2 cos 10 pointing vertically upward, so it's positive, plus N2 cos 10. The whole of this is equal to 0. So we said earlier, F3 is mu 3 N3, which is equal to 0.35 N3 because mu remains the same at all surfaces. So in place of F3, we have minus 0.35 N3 minus 1000 minus, in place of F2 remains 0.35 N2 multiplied by cos 80, and cos 80 gave us 0.17, okay, plus N2 cos 10. Cos 10 gave us 0.898 N2, and this is equal to 0. All right, so now, not forgetting, N3 is equal to 0.51 N2. So in place of this N3, we'll put in the value as 0.51 N2. That will automatically change everything here to N2. So we have minus 0.35. In place of N3, we have 0.51 N2. Okay, put down minus 1000 minus, now let's obtain 0.35 multiply 0.17. That gives us 0.06 N2 plus 0.98 N2, and this is equal to 0. So let's evaluate. Minus 0.35 multiply 0.51. That gives us approximately minus 0.18 N2 minus 1000 minus 0.06 N2 plus 0.98 N2, and this is equal to 0. So what we'll do at this point is, let's collect like terms, bring all the terms that contains N2 together. So I have minus 0.18 N2, okay, I have here minus 0.06 N2, I have plus 0.98 N2, then I have minus 1000 here, minus 1000, and this is equal to 0. So we can now evaluate this. So let's obtain minus 0.18 N2 minus 0.06 N2 plus 0.98 N2. Okay, that simply gives us, let's continue here. That gives us 0.74 N2 minus 1000 to be equal to 0. So we can simply say minus 1000 over to this side of the equation. We have 0.74 N2 to now be equal to negative sign plus an equal sign becomes positive. This is now equal to 1000. Now we divide both sides by what? Coefficient of N2 to make N2 subject. Therefore, N2 is now what? 1000 all over 0.74. So if we do this, we can now obtain the value of N2, the normal reaction 2. So 1000 divided 0.74, that gives us 1351.4 newtons. Okay, so the normal reaction 2 is simply 1351.4 newtons. So if you have this to be your normal reaction, you can now substitute into equation 3 to find the value of that horizontal force P. So let's do that and see. Substituting that into equation 3, we can now find the value of P, which causes what? The motion. So P is equal to 0.83 multiplies N2, and N2 is 1351.4. Okay, so this simply implies that the value of P is simply equal to, that gives us 1121.7 newtons. Okay, so this is now the value of P, which is required to raise the block B in figure 5. That's the value of P, 1121.7 newtons. All right, guys, so that's it on question 5. In the next video, I will see you on question 6. Thanks and cheers.